Okay, I'm going to start off today. So welcome to this webinar provided by the EPSRC Future Composites Manufacturing Research Hub entitled Rapid Composite Processing Technologies. My name is Alex Hammond from the University of Nottingham and I am the Hub Deputy Manager. I will be your chairperson today instead of Ole Thompson. Ole sends his apologies, but he is not able to attend, unfortunately. Before I introduce the speakers, please note the following. A recording of the webinar will be sent to those in attendance and also put on our website. Questions can be submitted via the Q&A facility at the bottom of your Zoom screen. Participants should put the name of the speaker their question is directed to at the start of their submitted question. I will read out selected questions which will be answered by the speaker at the end of each presentation. We will try to answer as many questions as possible within the allocated time. Our first speaker today is Professor Nick Warrior, Hub Director and Professor at the University of Nottingham. Nick will give an executive summary of the Hub at midterm point.
Thanks, Alex. Good afternoon, everyone. Thank you for joining today. I'm going to be giving a quick overview of the Hub, reflecting on its current status at the midterm point. So the Hub's a significant investment in composites manufacturing research by the EPSRC. It's over £10.3 million over 7 years. I'm going to advance this. Yeah, so the Hub objectives then, we got 4 objectives. We wanted to deliver research excellence in composites manufacturing. We want to deliver these research findings to industry via the High Value Manufacturing Catapult Centre network. We want to train early career researchers in PhDs, NGDs and postdoctoral work. The NGDs are trained via the EPSRC Centre for Doctoral Training in Composites Manufacturing at the University of Bristol. And we want to build national and international networks and develop collaborative research programs. So here are academic partners. To date, we've got 15 academic partners who've collaborated in research projects in the first half of the Hub. And we've got 37 industrial partners and 4 Catapult Centre partners. And we're very grateful to all of them for their support. So since the Hub started in 2017, the typical funding route for an academic institution is to apply for a feasibility study at one of our open calls. And you can see the call dates on the slide here. These are 50K 6-month studies, and on completion, the researchers can apply for core project funding, which is a 36-month collaboration of a value of around 500K. So we've got 29 funded projects, including 19 feasibility studies, 6 core projects and 4 fellowships. In addition, there are 28 leveraged PhDs and 39 NGDs. The projects are all within our research theme framework, where a project can be high rate deposition and rapid processing, designed for manufacture via validated simulation, multifunctional composites and integrated structures, inspection and in-process evaluation or recycling and reuse. So to maximize the synergy between the projects, to ensure the best practice sharing and to avoid repetition, we're using a workstream project management approach. Each workstream is a particular technology and is led by a national leader in the area. All projects are connected to a workstream and the workstreams feed into the research themes. So you'll see quite a lot of interaction across the portfolio. In the next 8 slides, I'll give you some research highlights from the different work streams, but I think you can see on this slide the level of crossover between the work streams and the research themes. So next slide, please, Claire. So work stream 1 is automated fibre deposition technologies. Nottingham and Bristol are working together here. Bristol is extending their continuous toe shearing research to process reclaimed or recycled fibre material using their hyperdiff process. At Nottingham, a novel experimental rig has been constructed. This rig can closely emulate commercial tape laying processes. The rig will be used to study process parameters and expand the operating range. So the DAISY diagram here shows how the projects in a work stream are connected. So work stream 1 connects a core project to an individual, an innovation fellowship and 5 feasibility studies. The industry and the host institution contributions provide the PhD and NGD student funding. Next slide, please, Claire. So work stream 2 is optimization of fabric architectures. Nottingham is working on developing a multi-scale modeling technique linked to a multi-objective optimization framework. This is based on geometries and meshes created in the well-known TextGen software. Manchester is developing complementary fiber placement techniques and machinery to manufacture multi-axial 3D preforms. So the team has demonstrated over 10% weight saving compared to optimized non-crimp fabrics. Workstream 2 links the optimized core project to 3 other core projects and a feasibility study. Next slide, please, Claire. So Workstream 3 is multifunctional structures. Imperial College has developed a structural composite sandwich panel which can be used to store energy as a supercapacitor. These panels are produced by embedding carbon fibers in a carbon aerogel. Imperial College is working with Bristol to develop a novel printing process to produce a textile with discrete regions of carbon aerogel structure, which can be shaped into a 3D preform for liquid moulding. Bristol's using its explicit finite element forming expertise to develop a specific modeling approach for these structures. Next slide, please, Claire. Workstream 4 is online consolidation, and the layer-by-layer process aims to combine the laminate layup and the curing steps to significantly reduce the manufacturing time and also to mitigate the risk of exotherm. Cranfield and Bristol are working, developing a fully coupled thermal consolidation, thermomechanical 3D simulation of the layer-by-layer process, and we'll be constructing a laboratory-scale pilot plant. James Kratz will be talking about the layer-by-layer project in more detail later on this afternoon. Next slide, please, Claire. Workstream 5 is liquid moulding technologies. So these technologies offer significant rate improvements over autoclave-based manufacturing processes. However, there are variabilities in the preforming and moulding aspects, and there are limitations in existing simulation techniques. So a collaboration between mathematics and engineering at Nottingham is developing Bayesian inversion algorithms, and these will work in real time to detect defects during the moulding stage using in-process data. A correction will be applied to process parameters to eliminate the defects. And there's some images here that Michael's presented to sort of demonstrate that sort of approach. Next slide, please, Claire. Workstream 6 is composite forming technologies. So the mechanics of fabric deformation in forming has been developed to an advanced level, but defect formation and forming limits are not clearly characterized yet. So in this project, Bath, Cambridge and Nottingham will work together to deliver enhanced experimental material characterization methods and high fidelity explicit FE simulation techniques to enable 3D form composite components to be manufactured from woven and non-crimp fabric textiles with a high degree of precision. So Lee will be talking about the forming project in his presentation later on this afternoon. Next slide, please, Claire. So Workstream 7 is microwave processing technologies. These have long promised great potential for increased control and reduction in curing time, as well as a reduction in processing power requirements. However, significant technical and safety challenges persist, and Workstream 7 aims to research microwave manufacturing technologies by modeling and by laboratory experiments aiming for material deposition rates in the range of up to 100 kilos an hour. So Workstream 7 is led by Wrexham Glyndŵr as a combination of smaller projects, including three feasibility studies. Next slide, please, Claire. So workstream 8 is the last workstream, and this is thermoplastics processing technologies. So thermoplastic composites offer huge potential for high volume applications because of their rapid consolidation, their multi-stage forming, or the possibility of multi-stage forming, and their jointing by welding and relative ease of recycling compared to thermosets. The aim in this work stream is to accelerate the UK activity in this area. And there's a hub thermoplastics working group that's been established to generate applications for funding in this area. So you'll see some of Warwick Manufacturing Group's work here with Neil later. So last slide, please, Claire. So that brings the current research up to date. So what do we plan to do for the next 26 months? So from our unallocated funding, we plan to offer another round of feasibility studies with one further core project. We anticipate that this project might be in thermoplastics, possibly over moulding, and that there will be increased interest in sustainability-based work in line with the net zero 2050 ambition. So thank you for joining today. Please have a look at our website, simcomp.ac.uk, for any updates. Thank you to all of the hub partners, the industrial partners and the academic partners and staff. And last but not least, I'd like to thank Fluency Marketing, the hub dissemination partner, whose artwork I've used in the presentation today. So thank you very much. I think we have some questions now.
There aren't any questions asked yet. So I think we'll move on to the next speaker. Thank you, Nick.
Okay, thank you.
Our next speaker is Dr. Neil Reynolds, Hub Researcher and Senior Research Fellow at the Warwick Manufacturing Group. Neil will present on the Hub feasibility study, Optimised Manufacturing of Structural Composites via Thermoelectric Variothermal Tooling.
Good afternoon, everybody. Yes, my name's Neil Reynolds. I'm as Nick said and I said, I'm a Senior Research Fellow in the Warwick Manufacturing Group. A very brief introduction to the group. So this project is being carried out within the Materials and Manufacturing Directorate within WMG. It's headed up by Prof. Tom Pies, who joined us just over 18 months ago. And he's heading up the National Polymer Processing Centre initiative. So within the MPPC, there's a portfolio of projects being established across the TRL MRL range from EPSERC through Catapult and up to Innovate UK towards exploitation. And we're looking at sustainable polymer solutions for sort of very high volumes, so things like polymer packaging, but also relevant today, low emission mobility, so structural lightweighting, metal replacement type materials. Next slide, please. So variothermal tooling, it's an area that we've done some previous research in, and it refers to tooling that we can rapidly vary the surface temperature of the tool using various means. And the point of this project is to determine if we can use thermoelectric modules to do the same thing. So basically, it's a Peltier module. The reason we're interested in the variothermal tooling is it allows us to very rapidly vary the surface temperature of a tool, so we can basically melt process thermoplastic polymers isothermally prior to then cooling them in a controlled way. The advantage of that is we can get to very short cycle times while still maintaining an isothermal process window. So the advantages of a thermoelectric module would be that the actual heating and cooling element is in direct contact with the tooling elements. That's the tooling surface. So there's a thermal couple, and we can use the thermoelectric module to manage the heat flow. So we can actually store and reuse heat energy between cycles. So quite a lot. There's existing technology that uses fluid coupling for the same thing, so air and liquids to move and to heat tooling surfaces. But the idea here is to actually move the heat around in the tooling system. So the key research areas are firstly an evaluation of the suitability of the Peltier technology in terms of things like heating and cooling rates and the maximum temperature, looking at things like the process energy requirements, and then how we actually control the system. And of course, there's some scientific objectives as well to see what the resultant properties of the material are. Next slide, please. So very quickly, on the right hand side, you can see a typical process breakdown for this variothermal process, where we have three key stages. We have a preheat stage on the left, a melt process stage, and a rapid cool. And looking at the schematic graph, we have temperature versus time. You can see there's a rapid increase in temperature, a hold during the melt process, and then a rapid cool. Looking at the left-hand diagram, where you can see the different tooling elements, you have the upper tool surface, which is 2 to 3 millimeters thick, the active Peltier element in the middle, and then a heat sink behind that. And that's what I was saying about you can effectively move the heat around within that system to process the material. Next slide, please. So an example of a Peltier shown on the right. It's typically 40 by 40 millimeters square. The approach we're taking is to try the technology on a 1D scale, as we're calling it, so a single module, to generate, effectively formulate our control and measurement strategies, and doing some parametric studies, and then very quickly moving on to a 2D system where we've got an array of modules working to globally and locally vary the temperature of the tool surface. You can see, hopefully, the video on the right shows that kind of assembly. And that will allow the sort of the end goal of the project is to do some flat to flat level trials and demonstration to see how the technology actually works. One thing to note is that we are using off-the-shelf modules which are actually built for cooling and energy harvesting applications. So regarding the robustness and the sort of heating and cooling speed, they are not necessarily built for this purpose, and so we are partnering with European Thermodynamics within this feasibility study and discussing how we could actually make bespoke modules for this application. Next slide, please. So the first part of the work we completed is 1D study on a single module. You can see the stack in the bottom left picture. You've got the tool surface and the Peltier module in the middle, and then the heatsink behind it. We've done this. The data shown here is an example cycle for a polyamide 6 process with no material, just the tool surface. So we're going from 240 degrees down to 170 and then back up. So the middle graph shows temperature versus time at the tool surface and the rear plate, and you can see that we can get down to and back up again in about 100 seconds, which is very encouraging. It's faster than the existing variothermal technology we've been evaluating. On the right-hand side, that shows us the actual cooling and heating rates. So in blue, the cooling rate shown on the right-hand side of the right-hand graph, going down to about minus 3.5 degrees a second. The efficiency drops as the temperature differential drops. It goes down to about 1 degree a second, cooling and heating. But the sort of take-home message from this is we can do as I said, the whole cycle in about 100 seconds. So if you were to include a dwell in there, you could probably do the whole thing in about 3 minutes. Next slide. So we're now in the middle of the 2D coupon study. You can see the apparatus on the right-hand side. It's a 2x2 array of Peltier modules. We're looking at polypropylene and polyamide 6 UD tape laminates. So they're going in dry, and then we're doing the full consolidation under a vacuum bag. And we're measuring the temperature at the tool and inside the material and establishing key criteria such as maximum minimum cooling rates and as discussed, the actual characteristics of the modules themselves. Could you move to the next slide, please? So these are the results from the actual coupon testing. So if you look at the graph on the right, you can see in orange the temperature versus time for the tool surface, and then in blue the mid plane of the 2 millimeter thick laminate. And you can see that I've divided the graph into 3, so you can see the heat processing cool stages. There's about just under 60 seconds dwell in the middle, and we arrived at this cycle time based on visual inspection of the laminate, so basically trying to manufacture a fully consolidated laminate. The parameters that we've used have translated into a total process time of about 400 seconds, so 6.5, 7 minutes. So certainly under 8 minutes we can do a full heat cool cycle on a single-sided heating system. And that the bottom right graph shows us that heating cooling rate we achieve at the tool surface and in the material. Because the materials are a relatively good insulator, actually in the mid plane of the material we're only seeing heating and cooling rates of about 1 degree a second. what's interesting about this, on the right hand side of the in the cooling stage, in the top graph, you can see hopefully a little bump, which is actually the crystallization exotherm that occurs during cooling of the polypropylene. And we think this is quite interesting. So if we move to the next slide, we've done the same analysis on the polyamide material, semi-crystalline material, and you can see the data from a cooling stage on the right hand side, where we've got in green temperature versus time, but the black line shows the actual cooling rate versus time, and effectively the cooling slows down during that crystallization stage, and you can effectively see the onset, peak, and end of crystallization. And replotting that data, as you can see in the bottom right hand side, you can actually see it's almost like a DSC trace, for those who are familiar, where you're actually plotting temperature versus cooling and heating rate, reading from right to left. So as the material cools, you can see the onset temperature, the peak temperature crystallization for that particular cooling rate, and then at the end of crystallization, of which you could demold the material. So we're in the middle of doing these parametric heating cooling trials for these materials, and the next stage is going to be to take the resultant material and do some microstructural and DSC measurements on that material. Move to the next slide, please. So this is on the right hand side, you can see our outline design. We're actually looking at for the prototype for this system, we're looking at a two-sided system, which would probably give us much better heating and cooling rates and more industrially relevant, because we're seeing a lot of thermal losses, as you'd expect from single-sided tooling. So that's the design that we're currently working on at the moment, and starting to create a bill of materials. But the ultimate conclusions are that we've developed this 1D and small 2D systems that have shown certainly sub-8 minute cycle times for a 2mm thick structural laminate, which is very encouraging. It shows that the technology might have an interest. And of course, there's this potential control of crystallinity that we could do, you effectively measuring the onset and peak crystallization during process. So there could be some real-time control aspects introduced into this system that we think is of interest. So that completes the presentation. So thank you for listening, and I'd like to ask if you've got any questions.
So there is one question, Neil, from Alistair Barnett. How scalable do you see your variothermal technology being? And are the modules cost effective compared with current variothermal technologies?
So as I said, the modules are off the shelf, so they are very cost effective, but we do have concerns because we're using them for heating at this stage, as well as the cooling. They're not particularly efficient. So we're not. We think that we're talking to our partner to see if there's a more appropriate system we could use for the active heating stage, and that might have some bearing on the robustness as well, because we are taking these modules up to very high temperatures. So they're effectively made, and the things like the solder are selected for a peak temperature of about 250, which is the upper limit for what we want for something like polyamide. So I think there needs to be some development, and we are talking to the partner about how we could perhaps come up with a more robust system, and perhaps use some conventional resistive heating on the heatsink side. So effectively, we do the heating into the heatsink and then use the Peltier module just to shuttle the heat around within the tool, rather than actually using the Peltier as a heating module. So that's sort of that side of it. From a scalability, there's lots of questions. Obviously, it's a very low sort of TRL feasibility study at this stage. There's questions regarding things like the flatness. Obviously, at the moment, everything's 2D. So can we make Peltier modules that aren't flat? That would be an obvious question. So I think in terms of scalability and cost, I think there could be a potential that, you know, these modules we're using at the moment are only 10 or 15 pounds each. So certainly watt for watt, they're competitive. But what we don't know yet is the longevity and sort of the mean time between failure, for example, of one of these systems.
Okay, thank you, Neil, and thank you, Alistair, for your question. We'll move on now to our third presentation. So our third speaker is Dr. Lee Harper, Hub Manager and Associate Professor at the University of Nottingham. And Lee will present the Hub Core project entitled Design Simulation Tools and Process Improvements for NCF Preforming.
Okay, thanks, Alex, and welcome to the presentation, everyone. Thanks for joining us. Hopefully I can advance the slides. So as Alex said, this is an overview of a new core project in composite forming that involves Nottingham, the University of Bath and the University of Cambridge. So as the title suggests, the aim is to provide process improvements and simulation design tools to enable composite designers to produce parts more efficiently and with greater confidence. And this project is exclusively looking at non-crimp fabrics, both biaxial and unidirectional materials. And this is being driven by our industrial partners from both the aerospace and the automotive sectors. And we're exclusively also looking at double diaphragm forming as a low-cost method for producing large-scale components with single-sided tooling. So there are 4 objectives for this work. The first is to further the fundamental science of fabric deformation for this family of non-crimp fabrics. The second is to look at developing more robust testing methodologies to be able to characterize these materials. The third is to develop practical simulation tools that can be readily adopted by our industrial partners so they can implement them to improve rate and robustness. And the fourth is to develop practical process changes, again, that can be easily implemented at an industrial level for both double diaphragm forming and non-crimp fabrics. So this slide shows how the 3 partners are integrating and working together. So the University of Bath will be looking at developing an analytical model for ply layup to establish a compatibility index for the selected layup based purely on the angles between plies to indicate wrinkles. And this is based on existing work at Bath for UD prepreg, which will be extended to look at unidirectional and biaxial NCFs using this eigenvalue energy minimization approach. The work at Cambridge is looking at developing a component geometry designer. Again, this is a tool that will hopefully be adopted by designers to bring them closer to the manufacturing space so that they can ensure that designs are produced so that they're fit for manufacture. And this is based on a machine learning approach using the output from finite element simulations. So this is a multi-parameter remodeling tool that relies on machine learning to train an algorithm to detect the location of defects to facilitate the rapid redesign of tooling where required. And then the third element of the project is at Nottingham looking at more detailed finite element analysis for defect prediction. And the objective here really is to focus on large structures, sort of 10 meters plus, so that we're able to detect small scale defects in the order of millimeters over that large length scale. So we're working with a group of industrial partners, so Dassault System, Hexcel Fabrics, Reinforcements in Leicester, GKN Aerospace and Gordon Murray Design. And the aim is to provide a range of process developments to improve the robustness of the double diaphragm forming process, whilst looking at locally tailoring fibre architectures to achieve a step change in formability. So if we have a look at, first of all, at the component geometry designer, this is the ongoing work at Cambridge, and this builds upon a feasibility study that was funded by the Hub at Cambridge around 18 months ago. And that work was concerned with developing methods for evaluating wrinkles within preforms. And Michael and the group at Cambridge developed a digital image correlation approach for measuring the amplitude of wrinkles. And they produced a nice forming rig towards developing a forming limit diagram for these materials. So the idea is now that we use this convolutional neural network as a means of applying machine learning to try and understand why defects occur as a result of features within the tool geometry. So on the left-hand side, you'll see this geometry generation algorithm, which is based on a series of polygons. And Werner, the PhD student, has developed this so that we can generate quite a diverse range of geometries that can be evaluated using the sort of simplified finite element approach that we've been working on at Nottingham, and other codes that are available within the community. So each one of these geometries will be evaluated for wrinkle patterns, looking at possibly the strain distribution in the fabric, and looking at overshearing and wrinkles that occur, and then they will be analyzed using an image analysis technique, and that information will be then fed into this deep learning model. And the idea is that that deep learning model will then be applied to a number of unseen geometries to try and predict the wrinkling patterns, and this can then be validated using the double diaphragm forming facility at the University of Nottingham. Moving on to look at the more detailed FEA analysis, this is building upon work at Nottingham. So some years ago, we had a project looking at developing a simplified finite element model using a membrane approach. More recently, we've been trying to incorporate the bending effects of the fabric plies. So sorry about that. So what we're using is this composite layup module within Abacus, where we can define a single ply using this laminated approach. The yellow region you see on the left-hand side represents the in-plane stiffness of the material, and then the grey outer regions represent the bending behavior, and we can therefore decouple the in-plane and the out-of-plane responses to account for the different stiffnesses. And we've, in addition to developing the model, we've modified the existing method for characterizing the bending behavior of these fabrics so that we can capture the non-linear behavior, and that's shown on the right hand side. You can see if we compare the two model outputs on the left with the experimental data on the right, the non-linear bending behavior gives a much closer response to reality in terms of the wrinkle pattern. So what we want to be able to do is use this more sophisticated, detailed model to be able to predict the location of wrinkles, but it isn't really practical to do that over large length scales because of the computational resource required. So we've looked at using this global to local modeling approach, whereby we can model small regions in great detail, but initially we do this global model using the lower order membrane approach to identify where the critical regions are. So in the center here, you see these plots. The left-hand column is the response of the fabric showing areas of overshearing. The central column shows areas where the fibers are in compression along the fiber length, which will lead to buckling and out of plane wrinkling. And then the third column shows areas of fabric bridging where it hasn't conformed well to the tool. So when those three are superimposed, we get this defect plot on the right-hand side, and we can use that information then to identify these sub-regions where we can apply the more detailed model. And that's what we're showing here with these simulations. So across the bottom, this is the output from the structured white light scanner where we've done the experiment and then captured the wrinkle patterns in the lab. And the simulation is showing these sub-regions that have been formed. So what we've had to do is we've ran the global model using the membrane approach and then extracted appropriate boundary conditions for these sub-regions. And you can see there's very good agreement between the predicted wrinkle pattern and the experimental shape below. And to confirm this, we've actually done some experiments using the same size and shape piece of fabric as in the submodel to demonstrate the importance of the correct boundary conditions. And we get a very different response if we form, obviously, a small piece of fabric such as this, because we don't get the same draw-in that we would get from a much larger piece of fabric. So the idea is that we have this toolbox and we want to then apply these tools to make local and global process improvements. So Shuai Chen is working on this multi-objective optimization algorithm using genetic algorithms, and the idea is we can then intelligently modify the preform and the process to hopefully reduce or mitigate against these defects. So the things we're looking at are intraply stitch removal. You can see here the red regions indicate where the stitches have been removed, and this has a positive influence on the wrinkle patterns of these preforms. The idea is by using that genetic algorithm, we can then intelligently modify the stitch pattern to get a good balance between mechanical performance, formability, and handleability of the ply. Similarly, we've looked at local deposition of resin to try and change the local shear stiffness of the fabric, and this will then be driven also by that genetic algorithm. And the resin can also be used to locally bind plies together. And then finally, we've been looking at the influence of friction, interply friction, whereby looking at adding lubricants and other materials between the plies, we can influence the coefficient of friction, and this has a positive effect on the wrinkle behavior of the ply. So this seat mold here, for example, at the top, you can see there are quite severe wrinkles around the perimeter, but when the fabric has been lubricated, those wrinkles disappear. So thank you for listening, and I'm happy to take any questions.
Right, there aren't any questions currently.
Okay.
So we will move on to the next presentation. Thank you very much, Lee. So our final speaker today will be Dr. James Kratz, Hub Investigator and Lecturer at the University of Bristol. And James will present the Hub Core project layer by layer curing.
Thank you, Alex. So today I'm presenting on behalf of the other Alex. So this is Alex Skordos, who's leading the project at Cranfield University, and I'm based at the University of Bristol, and we're working together to try and bring the concept of layer by layer curing to fruition. So I'm sure everyone's aware that most composite processes can be broken down into three main steps. The first one is depositing fibers, whether they be dry or wet, consolidating the layers together, and then curing the polymer and or solidifying a thermoplastic. And these have historically been kept as discrete segments. Makes us ask some questions. Why have they been discrete all the way through history? Is it because of the size of the components that were originally made by hand layup? And as we get into bigger and more automation being used, would merging them together bring some sort of positive benefit? So we like to think that there's three main benefits to using layer by layer curing. Removing debulking, no exotherms in thick components. And also, it would be great if we could just get away from the bottleneck that is the autoclave. And there's definitely a few other positive aspects as well, including limiting out time of pre-preg materials and possibly introducing online inspection. Now, this sounds really great, but there's definitely a couple of really big research questions around interfaces, consolidation, and dimensional stability of the components that we might want to make. So to take a look at these three important aspects, I've got an example on the right-hand side of the screen. We can see a partially cured substrate with a couple of uncured strips being applied. So the first question is, will the uncured layers stick to the partially cured substrate? When we try to apply layer by layer curing, will the laminate that we've made in the end have the desired fiber volume fraction and low porosity that could allow us to replace autoclave type processing? And then finally, around the concept of residual stresses, is it going to create a warpage that's undesirable? So you might imagine that if you've got your first ply oriented at the 0 degree direction, and then it's partially cured, and you put a 90-degree ply on top of that and cure it, once you release the pressure, are we going to end up with a saddle, or are we going to end up with residual stresses that are so severe that we can't continue the process? So I'm going to walk you through a case study that I'm hoping will identify some of the issues that we're going to try to tackle, and show you that we have some technology a little bit further. So if we're trying to make a thick composite laminate, conventional curing tends to lead to a very high exotherm. So if you think about a single dwell process for a thick laminate, you tend to have a really significant overshoot in temperature just due to the, the curing of the polymer and the low thermal conductivity of the matrix. And one of the common ways to alleviate this problem is to increase the length of the process cycle. And you can either add multiple dwells, slow the ramp rates down. There's even the possibility of a thermal cooling. So all of these things then tend to increase the time. So what we need to be able to do, or what we're hoping to be able to do, is to intensify the process and save time as well. So the way we looked at that with layer by layer curing is we started by creating a digital twin of our process. We broke the laminate down into a series of sublaminates, where the first layer would see the pressure and temperature of the entire process, but the final layer, so layer N, would only see one temperature and pressure cycle. And if we run our digital twin, where we've coupled the consolidation and the curing together, we can see that it's always going to be more effective for thick laminates to approach this problem with a sublaminate type solution. So if we look on the right-hand side, we can see cure time as a function of temperature overshoot. And this is for a target cure of 120 degrees centigrade. So within our conventional process, we can run a series of solutions, and the minimum tends to become the Pareto front. And by examining the layer by layer process run at a couple of different boundary conditions, so the gray X will show you how, if we wanted to process the component in an hour, we could do that, but we'd have a 50 degrees centigrade overshoot. Processing the component in 2 hours, not as severe an overshoot, but 15 degrees centigrade. And potentially, we have the ability to take advantage of that to achieve our target process temperature. So when we actually manufactured a 300 ply laminate, it was 100 millimeters by 100 millimeters. So I have it here, proof it really does exist. There's also a photograph in the on the slide. And we were really quite impressed. The volume fraction was fairly good. This was processed at 1 bar. Yes, it was a flat plate. We processed it in a test machine where the platens were kept at a constant temperature. So this gave us really good control of the thickness that we were trying to achieve and the pressure. Now, if you look at the temperature versus time plot in the center of the graph, you can see how that first sublaminate experiences the cyclic temperature through the process. And as we add sublaminates, they'll have fewer consolidation and temperature cycles, but they tend to have that 15 degree centigrade temperature overshoot. And if our target process temperature is 120, we're actually within about 5 degrees centigrade. So marrying up the traditional manufacturing targets. And I'll remind you that this process took a little over 2 hours, but it was still a good 30 or 40 minutes faster than a conventional process. I'll just note that there was no debulking applied whatsoever in this instance. So we just laid up the laminates, chucked them into the press, squeezed it at elevated temperature, and the results that you see are the results that we obtained. And through testing of what happens in the interfaces, what we were able to identify was that if we are able to keep the degree of precure of the sublaminate to gelation or a little bit lower than gelation, we can preserve the interlaminar properties measured by double cantilever beam testing in blue or interlaminar shear testing in black. And examining the microstructure using an optical micrograph, we can see that we've got fairly even thickness between plies, but there are some darker areas that look a little bit suspicious. Now, initially we thought these were voids, but by zooming in a little bit closer using an SEM, we were actually able to identify that it's the microstructure of an additive that was introduced into this material. And the same microstructure is visible in an equivalent autoclave cured laminate, but the sizes are a little bit different. So with layer by layer, we have intensified the process, and we need to keep an eye on whether or not we're actually changing the microstructure of the composite and whether those properties are equivalent to a baseline. But overall, the quality looks really good, the porosity is fairly low, and the interlaminar properties are there. So to summarize, we're trying to bring deposition, consolidation, and curing into a single manufacturing process. We're looking to eliminate debulking and exotherms and the autoclave. We've proven that it's possible on a fairly small but very thick flat laminate. And we're just starting the journey now to take this into the automated space. We've got some great project partners, including large companies, small, medium-sized businesses, another university, and the National Composite Center, part of the High Value Manufacturing Catapult. EPSRC is supporting some of the work at Cranfield and Bristol through the SimComp grants. We've got in-kind PhD and Eng.D researchers, and we're expecting a good interaction with our industrial partners. So we've managed to have a kickoff meeting during lockdown, and there's a very strong excitement around this activity. We're in the process of designing rigs that are going to allow us to do continuous processing in an automated fashion. So at Bristol, we're going to focus on automated fiber placement, and at Cranfield, the activity is going to be centered around filament winding, possibly some pultrusion, maybe even a combination of the two. So we need to look at some new materials. We've got some existing materials in the toolkit aligned to the specific project partners, and we are beginning our journey. Well, we've just started the journey, and we'll be taking that through to the next about 3 years. So with that, I'd like to thank you for your attention. If you have any questions, feel free to ask them now, or feel free to get in touch with either Alex or myself at any point in the next 2.5 to 3 years.
Thank you, James. So there's 2 questions for you. One from Pascal Hubert, and he says, is this approach only limited to press molding? Other heating sources possible, i.e. infrared?
Absolutely. That is a great question, Pascal. Obviously, one of the advantages of press molding is it's fairly simple. So to be able to get this concept demonstrated, that's the approach we took. When you go to automation, we have to consider how the melting of how really dropping the viscosity of the thermoset is going to contaminate any end effectors. So our aspiration is to go to double curvature complex geometry. And in terms of heating solutions, infrared could be a very good option. However, one of our project partners is Heraeus Nobolite, and they've developed this really great flash lamp technology that has the same heat up rates as laser, but it doesn't require a concrete room. I mean, it does have some ultraviolet issues that need to be addressed from a safety standpoint, but we're looking to work with them to try and upscale the to provide the right amount of heating and the right latency, because the challenge with infrared can sometimes be it's just not fast enough.
Okay, and then the second question is from Martin Armstrong, and he's just queried the pressure used and duration.
So the pressure used in our proof of concept was the equivalent of 1 atmosphere. And the duration, I think each cycle was about 10 to 12 minutes. And there was about a 2 or 3 minute swap out during the process, where we had to open the press, put the new block in, set some certain things on the computer, click go, and then apply the squeezing again. But during that entire stage, the temperature of the platens remained constant at either 110, or we even did one at 130 degrees centigrade.
Okay.
There's definitely room for shortening the process. This was done in the lab, so it was we were a little bit slower than if you had some sort of a nice, really automated process. It was a little mandrolic on our side.
Okay, thank you for that. And then we have another question from Martin Armstrong. And this is to all of the panelists, so I'm not sure you probably all want to unmute. But he's asking, what are the possibilities for flexible modules to allow the manufacture of complex tool shapes? So I'm not sure if anybody wants to answer that question.
I'll take a go first, since I'm here and my mic's on. The aspiration is to get to non-flat complex geometries. How complicated we can go will depend on the the automation that we're working with. Automation is great for larger, gently contoured components, but not super high complexity things that you might find on, let's say, a Formula One chassis, for example.
Would anybody else from the speakers want to add to that? No. Okay. In that case, then, that concludes this webinar. So I want to thank all of the speakers and the audience for joining us and for your interesting questions today. We plan on doing a series of these short webinars in the next year, and we'll send out further details soon. If you would like to provide any feedback from today's session, then please do so by sending me an email. We hope that you enjoyed today's session as much as we have, and bye for now.